So if you were to actually follow the classical laws of physics strictly to the letter, baking a pizza should be, well, a cataclysmic event.
Right, yeah. It should literally destroy the world.
Exactly. According to the foundational math of the 19th century, specifically this thing called the Rayleigh-Jeans law, heating up an enclosed object like a pizza oven should cause it to emit an infinite amount of high-frequency ultraviolet energy.
Which is obviously a problem.
Right. The moment you turn the dial to 400 degrees, the oven would essentially just vaporize the entire Earth. But obviously when you bake a pizza, you don't destroy the universe. Thankfully. But for a really long time, the absolute brightest minds in the world could not mathematically explain why. So today we are looking at the math that literally saved the universe.
It's just the ultimate paradox, isn't it? I mean, the classical physics that built the entire Industrial Revolution completely collapsed the moment we looked closely at something as simple as a hot, glowing box. We had to completely rethink what reality is even made of.
And that is exactly our mission today. Welcome to our deep dive from Newton to gravitational waves. And our goal today is to extract the ultimate aha moments from 10 landmark discoveries that entirely shifted humanity's understanding of space, time, and matter.
Yeah, it's a huge journey.
It is. Okay, let's unpack this because this deep dive is going to serve as your perfect shortcut to really understanding the hidden architecture of reality without, getting bogged down in unreadable equations.
What's fascinating here is that behind every single complex mathematical proof, there's a deeply human story of frustration and just intense curiosity. You're watching humanity transition from a dark age of explaining the world through these mystical occult qualities into an era governed by probabilistic waves, warped geometry, and hidden symmetries.
Yeah, to understand how we broke the rules of the universe, we have to start by establishing what those architectural assumptions even were in the first place. So let's look at Isaac Newton's 1687 Principia.
A massively important document.
Huge. Before Newton, science was largely just natural philosophy, dealing with unseen, almost magical forces. And Newton replaced those occult qualities with hard, deterministic math, proving that the exact same force pulling an apple to the ground is what holds the moon in its orbit.
Right, and to do this, he actually had to invent an early form of calculus. He called it the method of first and last ratios.
Which is wild on its own. But his biggest assumption was really about the nature of space and time, wasn't it?
Oh, absolutely, yes. The Newtonian framework relies on a very specific set of assumptions. So Newton argued for absolute space and absolute time. Time, in his view, is just an unchangeable metronome.
Like it's just ticking away in the background.
Exactly. It ticks forward evenly for you, for me, and for someone on the other side of the galaxy. And space is just an empty, rigid stage. It's completely passive.
Right.
The drama of matter, planets orbiting, apples falling, all of that plays out on top of this stage, but the stage itself never, ever changes.
And that deterministic clockwork view basically stood completely unchallenged for over 200 years. But then we hit the mid-19th century, and that rigid stage starts to hum. Scientists are realizing electricity and magnetism interact, but they lack a unified theory for it.
Right, they have the pieces, but not the whole puzzle.
Exactly. So James Clerk Maxwell reads Michael Faraday's work on invisible lines of force and decides he's going to rigorously translate that into mathematics. This is his 1864 paper, A Dynamical Theory of the Electromagnetic Field. But to do this, Maxwell creates a mental model that, frankly, sounds utterly bizarre today.
It really, really does. To construct his equations, Maxwell essentially imagined that the vacuum of space wasn't empty at all.
Right.
He pictured it filled with this complex, microscopic mechanical scaffolding, consisting of rotating fluid cells and idle wheels.
Wait, hold on. I need to push back on this.
Oh, for it.
So before he successfully proved light was an electromagnetic wave, Maxwell literally imagined the vacuum of space was packed with microscopic spinning gears just to make his math work.
He did, yeah. It was a heuristic, a mental bridge. He was trying to model physical stresses and strains in a vacuum, treating empty space almost like a mechanical machine.
That is just so wild to me.
But the brilliance of Maxwell's work is that this bizarre mechanical model led him to discover a concept called displacement current. He realized that a changing electric field in a vacuum acts exactly like a physical electric current.
Okay.
And once he had that mathematical piece, the scaffolding just collapsed. He didn't need the imaginary gears anymore. He had successfully combined electricity and magnetism into one framework. And when he calculated the speed of those electromagnetic ripples moving through space, it perfectly matched the known speed of light. That was the huge breakthrough. Light is just an electromagnetic wave.
I love that. If you're trying to picture this shift in reality, imagine you are sitting in Newton's rigid theater. Everything is isolated and disconnected. Maxwell's shift to a continuous field is like realizing there's this invisible tension humming through the air of that theater, connecting everything. We moved from things pushing each other instantly across empty voids, to waves rippling through these continuous, omnipresent fields.
But of course, this brings us right back to your pizza oven.
Ah, yes, the pizza oven of doom.
Right. Just as physics seemed to be perfectly wrapped up with these continuous wave theories, the blackbody radiation problem, which they called the ultraviolet catastrophe, broke the entire classical framework.
Because the continuous wave math predicted infinite energy. So how did we actually fix the oven?
Enter Max Planck in the winter of 1900. After years of trying to solve this infinite energy paradox with classical thermodynamics, he basically resorted to what he explicitly called an act of desperation.
Wow, an act of desperation.
Yeah, he proposed that the microscopic electrical oscillators in the walls of the oven couldn't emit energy in a smooth, continuous flow.
Right, they had to emit energy in tiny, indivisible, discrete chunks. He called them quanta. And they're governed by a tiny fundamental value we now call Planck's constant.
Which is mind-blowing.
It really is. It's like, imagine zooming in on a remarkably smooth, beautiful photograph of a sunset. Classical physics insists that no matter how close you look, it's a perfectly continuous gradient of color. But Planck zoomed in and realized, wait, reality is made of tiny digital pixels. The universe is actually pixelated at its foundational level.
That's a great way to put it. And the incredible thing is that Planck hated his own theory.
Really?
Yeah, he thought it was just a mathematical trick to fix the oven problem. He didn't think it was real. But he had accidentally birthed the quantum revolution.
Because you can't put the genie back in the bottle.
Exactly. By 1927, Werner Heisenberg takes this pixelated reality and formalizes it with his uncertainty principle. He proves mathematically that in this quantum micro world, there is a fundamental hard limit to what can be known.
Right, you can't know everything.
No, you can't. It is physically impossible to measure both the precise position and the precise momentum of a particle simultaneously.
Wait, I want to clarify something for the listener here, because the term observer effect gets thrown around a lot in pop culture. This isn't just a measurement problem, right?
What do you mean?
Like, it's not like the electron is a tiny billiard ball hiding in a specific spot, and our tools are just too clumsy to find it. The implication is that until it is observed, the electron doesn't actually exist as a tiny billiard ball in a specific spot, but just as a cloud of shifting possibilities.
Exactly, yes. And that is the profound realization made by Erwin Schrödinger and Max Born. Schrödinger wrote an equation describing the electron as a wave, and Born interpreted it as a wave of pure probability.
Pure probability.
Yeah, the wave just calculates the mathematical likelihood of finding an electron in various places when you look for it. But before you look, the electron is quite literally a smear of potentialities.
That is just so counterintuitive.
It is. The defined path of a particle only snaps into existence upon observation. So the rigid clockwork causality of Newton's universe was officially dead. At its absolute core, nature relies on chance.
So we have a massive logical conflict here, then. We have this jittery, probabilistic, pixelated, subatomic world. But what is happening to the macro world? Because while the quantum physicists were busy tearing down the microworld, Albert Einstein was simultaneously dismantling Newton's rigid stage on a cosmic level.
Yeah, Einstein was busy.
Very busy. Let's look at 1905, special relativity. Einstein starts from a simple annoyance regarding an asymmetry in Maxwell's theories.
Yes, this is such a cool detail. In Maxwell's framework, if a magnet is at rest and a conductor moves, a current is induced.
Okay.
But if the conductor is at rest and the magnet moves, the exact same current is induced. Yet the classical theory treated these as totally different physical phenomena.
Which bothered Einstein.
Deeply. Einstein argued that the laws of physics must look identical to all observers moving at a constant speed. There is no absolute state of rest in the universe.
And he also accepted a brutal truth. The speed of light in a vacuum is an absolute constant for everyone, no matter how fast you are moving toward or away from it.
Right.
Now, if the speed of light is an unyielding barrier, something else has to give to accommodate it. And that something is time and space. He proved the relativity of simultaneity.
Which is just a fancy way of saying time is relative.
Exactly. Two events that happen at the exact same moment for you might happen at entirely different times for someone zooming past you in a rocket ship. Moving clocks tick slower. Moving objects shrink in the direction of motion. Space and time are completely flexible, and of course E equals mc squared.
But special relativity had a glaring hole.
Oh!
Yeah, it only applied to objects moving in straight lines at constant speeds. It did not account for acceleration, and more importantly, it did not account for gravity.
Oh, right, because Newton's gravity was instant.
Exactly. Newton's concept of gravity assumed massive bodies instantly pulled each other across infinite space. But that instantaneous pull violated Einstein's new cosmic speed limit. Nothing can be faster than light.
Here's where it gets really interesting. Einstein wrestles with this for a decade, giving us general relativity in 1915 or 1916, depending on the publication. And he proposes that space and time are woven together into a single, flexible, four-dimensional fabric. Now, a lot of people use the analogy of a bowling ball resting on a trampoline to explain this.
I've heard that one a million times.
Right, but let's throw that out because it relies on pulling something down, which is just using gravity to explain gravity.
That's a really good point.
Instead, picture a globe in front of you. Imagine you and a friend stand on the equator 1,000 miles apart. You both start walking strictly, perfectly straight north.
Okay.
At first, your paths are parallel, but as you keep walking straight, you begin to drift closer and closer together until you finally bump into each other at the North Pole.
That is a phenomenal way to visualize it.
Right. No invisible force pulled you together. The geometry of the Earth's curved surface simply dictated your paths, and that is general relativity. Space-time is the curved surface. Gravity isn't an invisible rope. It is objects simply following the natural, straightest possible path, geodesics, through warped geometry.
And we really must emphasize why this shift is so monumental. General relativity changed the universe from a passive, empty stage into an active, dynamic participant in the cosmic drama. The fabric of reality itself can bend, ripple, stretch, and extend. The stage is part of the play now.
Okay, so by the late 1920s, physics has completely broken.
Pretty much.
We have two wildly successful but completely contradictory rule books for reality. For the cosmic stuff, we have Einstein's beautifully smooth, continuous, deterministic, warped spacetime. And for the tiny stuff, we have Heisenberg and Schrödinger's chaotic, pixelated, probabilistic quantum realm.
They do not get along.
Not at all. So the next massive leap in modern physics was the desperate attempt to unify these conflicting realities using the sheer logic of mathematical symmetry.
Yes, and this brings us to Paul Dirac in 1928. Dirac basically set out to mathematically describe an electron moving at a significant fraction of the speed of light.
Okay.
He successfully combined the math of special relativity with quantum mechanics into one elegant equation. But there was a massive quirk in his math.
Right. It's kind of like how in basic algebra, the equation x squared equals 4 has two valid answers, right? +2 and -2.
Precisely. Dirac's equation yielded two solutions for the energy of the electron. One solution described the normal positive energy electron we all know, but the other mathematically described an electron with negative energy.
Which is impossible, right?
Exactly. Classical physics dictated that negative energy was a physical impossibility.
So I have to ask, because in basic algebra, if you get a negative square root in a real-world word problem, you usually just throw it out as a mathematical artifact, a glitch in the matrix.
No, you ignore it.
Are you telling me Dirac saw a negative number in his algebra homework that defied all classical physics and common sense, and instead of assuming he made a mistake, he just trusted the math so much that he accidentally discovered antimatter?
He really did, because Dirac possessed this profound, almost religious faith in mathematical beauty. To him, the equation was simply too elegant to be flawed. So in 1933, he interpreted that negative solution to mean that for every fundamental particle, an exact counterpart must exist, an anti-electron, identical in mass, but with a positive charge.
That is just incredible.
It is. If we connect this to the bigger picture, this was an astonishing philosophical shift. Mathematics was no longer just describing nature after the fact. Its pure internal logic was actively predicting entirely hidden dimensions of reality like antimatter that humanity had never even conceived of.
Which perfectly sets the stage for Chen-Ning Yang and Robert Mills in 1954. So we are diving deep into the nucleus of the atom now, into a space a millionth of a billionth the volume of the atom itself.
It's unimaginably small.
And we discovered protons and neutrons aren't fundamental. They're basically just bags of smaller particles called quarks, held together by gluons. It is a chaotic subatomic zoo in there.
A total zoo. And to organize this zoo, Yang and Mills introduced something called non-abelian gauge theory. And the underlying principle here is internal mathematical symmetry.
Okay, I need some help here.
Sure.
I think most of us understand visual symmetry, right? Like the left side of a butterfly matches the right side. But what on earth is an internal mathematical symmetry in a quantum field?
Okay, let's use a geometric analogy. If you take a perfect square and rotate it exactly 90 degrees, it looks entirely unchanged.
Right.
The rules governing the square allow it to transform while maintaining its fundamental identity. That is a global symmetry. But in quantum mechanics, particles have mathematical properties like their quantum phase.
Okay.
Gauge theory basically asks, what happens if we demand that this mathematical symmetry holds true not just globally but locally at every single independent point in space and time, even as things shift and change?
Okay, so you are forcing the math to stay balanced no matter what happens.
Exactly. You demand the balance. And when you mathematically enforce that local symmetry, the equations become incredibly rigid. To keep the math balanced while the particle's internal properties shift, the mathematics absolutely requires the existence of compensating fields.
Like they just pop up in the math?
Yes. If you write the equations to demand symmetry, these fields mathematically pop into existence. And Yang and Mills discovered that these mathematical compensating fields correspond to the actual physical fundamental forces of nature.
That is deeply, deeply profound.
Yeah.
You are saying the fundamental forces of the universe, the strong nuclear force, the weak force, electromagnetism, they aren't just arbitrary physical rules someone wrote down on a piece of paper. They are the inevitable physical manifestations of mathematical symmetry demanding balance.
Yes, that's exactly it. Those compensating fields are called gauge fields. And this framework unified the electromagnetic and weak nuclear forces. It described the strong force, and it basically became the absolute bedrock of the standard model of particle physics.
Wow. Okay, so we've just spent a century making these incredible mind-bending predictions based purely on the faith that the math is right.
Right.
But our final milestone is about finally developing the physical technology to observe that math in violent cosmic action.
We were talking about gravitational waves.
Yes.
So a century ago, Einstein's general relativity predicted that when incredibly massive objects accelerate, they should literally shake the fabric of spacetime, sending these invisible ripples radiating outward at the speed of light.
But the stretching and squeezing of space is so unbelievably infinitesimal. Like, as a gravitational wave passes through you, it stretches and squeezes the space you occupy by less than 1/10,000th the width of a single proton.
It's absurdly small.
How do you even build a ruler to measure that?
Well, you build LIGO, the Laser Interferometer Gravitational Wave Observatory. You take these vast L-shaped tunnels stretching for miles in Washington and Louisiana.
Okay.
You fire a laser, split it down both arms, bounce it off mirrors, and recombine it. The lasers are perfectly tuned, so their light waves cancel each other out, creating total darkness.
Like noise-canceling headphones, but for light.
Exactly. But if a gravitational wave ripples through the Earth, it stretches one arm of the tunnel while squeezing the other by a fraction of an atomic nucleus. The lasers fall out of sync, the light waves no longer cancel out, and a sensor detects a flicker of light.
A flicker that tells us a cosmic catastrophe happened. Let's talk about the specific event that caused it. 1 billion years ago, in a distant galaxy, two black holes, one 36 times the mass of our sun, the other 29 times, became locked in a death spiral.
Oh, such a violent event.
Approaching each other at significant fractions of the speed of light, they finally merged. And in a fraction of a second, they converted 3 times the mass of our sun into pure gravitational wave energy.
The power radiated in that single moment was 10 times greater than the combined luminosity of every single star and galaxy in the observable universe.
That is just hard to comprehend.
And those silent ripples of warp geometry traveled across the cosmos for 1 billion years.
Until September 14th, 2015. That is the exact day the ripples washed over Earth and subtly shifted those mirrors in the LIGO tunnels, creating a distinct chirp in the data. Signal GW150914.
The first direct observation.
It is as if humanity had been watching a silent movie of the cosmos for all of recorded history, and suddenly we plugged in the audio cables and heard the universe's soundtrack for the very first time. We literally heard the fabric of space vibrating from black holes colliding.
It's amazing. It opened an entirely new observational window. But for all our triumphs, we must recognize the steep walls of our current ignorance.
Yeah, we don't know everything.
Not at all. We have the standard model governing the quantum microworld and general relativity governing the cosmic macro world, but they absolutely refuse to work together. We have no working theory of quantum gravity.
And when we look up at the night sky, we now understand that everything we can see, touch, or interact with, the stars, the galaxies, the gas clouds, that's just a tiny fraction of what's actually out there. We know from observing gravitational effects that the vast majority of the universe is made of dark matter and dark energy.
Right.
And we have absolutely no idea what they are. So what does this all mean? It means that true science always ends in humility. From Newton's rigid clockwork to literally hearing black holes collide 1 billion light years away, we've completely rewritten reality, but the universe still keeps its deepest secrets hidden in the dark.
And that reality leaves us with a fascinating, almost haunting proposition.
No.
Yeah. So we learned today from Heisenberg and Schrödinger that in the quantum microworld, the very act of observing a particle collapses its wave of probability and forces it into a definite reality. Given that roughly 95% of our universe is made of currently unobservable dark matter and dark energy, what happens to the very fabric of the cosmos on the day we finally invent the technology to observe it? Will uncovering the final missing pieces of the puzzle fundamentally change the universe we are looking at? Just like looking at an electron changes its path.
Wow. That is a staggering thought to leave you with. When you walk outside today and put your foot down on a concrete sidewalk, just remember it might feel solid and deterministic, but beneath the surface, it is a shifting sea of quantum probabilities and warped geometry just waiting for you to interact with it. Thank you for taking this deep dive with us today. Keep questioning the reality around you.